Okay, we're going to look at marking your Chemistry Unit 2, higher tier, May 2012. Make sure you get the benefit out of the hard work you've put into doing this. So in the first question there, it's looking at explaining in its position in the table whether indium is a metal or a non-metal. So we're looking at the periodic table in this question. The clue here is it's in group 3. You look at group 3 and you find indium. You find it down here, and it's well to the side. Here's where you'd have the little line showing whether things are metals and non-metals. Metals over here, non-metals over here on the right. So it's to the left of that line. So the main thing that you're looking at here is you're going to make a decision whether it's a metal or a non-metal. It's going to be a metal. Why? That's the position. It's going to be on the left-hand side of the periodic table. That gets you the 2 marks. Metal on the left-hand side. When we're looking at an electronic configuration for part B, this means it's going to have 2 electrons in the first shell, 11 left over, 8 electrons in the next shell, so that's 10 used altogether, 3 left over, and then it's going to have 3 in the outer shell. So you'd write that down as it is here in the mark scheme as 2.8.3. That's a total of 13 in total. When we're looking at isotopes, isotopes have got the same number of protons but a different number of neutrons. So when we're looking at boron, boron is an element. All the elements will always have the same number of protons. So boron is an atomic number of 5. It'll have 5 protons. For part 2 of the question, following on in a similar sort of line, where it's asking about isotopes, as I said a moment ago, they'll have the same number of protons. So in this case, boron will have 5, but a different number of neutrons. So if we look over here, and the clue there is that it's got boron 10 and boron 11. That'd have 5. 5 and 5 is 10. That'd have 6. 5 and 6 would make 11. This one here gives the reason why the relative atomic mass is closer to 10.8 rather than 11. It's just because there's more 11 than there is 10 for the easy answer. If you were having to do a calculation, you'd get a percentage, and let's say it was 50% of each. You'd find what 50% of 10 is, and 50% of 11, and add the 2 percentages together, and then that'd give you halfway. In this case here, it looks like there's going to be a much higher percentage of the 11 than 10. Scrolling down, question 2. So copper is a metal. Thinking about the structure of it, why can it conduct electricity? Well, the answer is the electrons D can move. You've just got to think of the structure of the metal. It looks like a solid. It's got those circles arranged in a regular pattern, just like a solid you draw in year 7. But each of those ones has got a little positive in it. It's a cation. The reason it's a cation, a positive ion, is because it's lost electrons. Metals like to lose electrons. They generally have like 1 or 2 electrons in their outer shell, and they want to get rid of them to make them happy. And then those electrons that are lost, they're delocalized, they can move around, they conduct the electricity. As always, your multiple choice questions are a little bit harder than you'd think because they do include a lot of possible right answers, and they ask you about quite difficult topics. Copper forms coloured compounds. The group of metals that form coloured compounds, well, you've only got 2 groups we've learned about in chemistry. So you're only guessing about group 1, alkali metals, or the transition metals. None of the others are groups of metals. Group 1's got sodium in it. Sodium chloride, that's salt. Is salt coloured? No. So it can't be alkali metals. What can it be? Transition metals. So we're looking at things like copper compounds, iron compounds, like hemoglobin in blood gives it the red colour. So transition metals form colour. If you get asked about colour for properties of things, it's transition metals it's asking about. So this one here, your question is about another group in the periodic table. So we've got that theme of groups going on. This one is about group 7. You've got chlorine. So when chlorine is going to dissolve in the water, it's going to form hydrogen chloride, which is hydrochloric acid. So hydrogen chloride solution is hydrochloric acid. And that's the main thing you're looking at. It's dissolving to form hydrochloric acid. 2 marks. Almost seems too easy. I've seen it before where they've put in universal indicator and asked what colour it would go and explain what's happening, and water would start rising up the tube as the gas dissolves and there's no gas left. Then the water would rise up to fill it up. So you might have to explain that in harder questions, but this one's only 2 marks. So when chlorine is bubbled into potassium bromide, the solution turns orange. Why? Again, we're looking at halogens. The reactions you've looked at for this are displacement reactions. What that tells me, because it's changed colour, it tells me that the chlorine is more reactive than the bromine, so it has displaced the bromine. So that colour change is because you get the orange bromine in the solution rather than the chlorine there. I remember the bromine, you've seen that before, bromine water in Unit 1, the test for alkenes, alkanes. Barium sulfate can be prepared as a white precipitate. Describe how you can do this. There's a few key little hints in the question here to help you with that. It says how you can make a pure sample, filter it. How we could make a dry sample, leave it to dry. Okay. There's a third mark available, and after pure and dry, the easiest thing that you can say is mix the two chemicals together. We haven't got complicated there. If you look at the mark scheme, mix them, filter them, wash them, dry them. No super science there at all. Okay. A lot of people think that's harder than it is. It really, really isn't. So on this one here, it's multiple choice, and again it's tricky because they throw in lots of possible answers. Cracking was Unit 1, so we know that's wrong, but that's where we got a long alkane and broke it into a shorter alkane and alkene. Displacement is what we're talking about with halogens, about swapping partners. There's no clues in the question for that. Oxidation is adding in oxygen, and precipitation is where you get the solid coming out. The clue here is that we have carbon monoxide here and it's carbon dioxide there. The difference is it's got more oxygen here, so it's oxidation, option C. Up here. For B, explain why the catalyst is spread on the honeycomb structure rather than used in large pieces. They're very nicely giving you the comparison. Why not large pieces? Large pieces would have a small surface area, so a honeycomb has a larger surface area, first point in the mark scheme. Because it's got a larger surface area, there's more surface available for collisions as part of collision theory, so the reaction will go faster. So you can just say a larger surface area, more collisions. Next bit. Hot gases pass over it. Why is the catalyst more effective when the engine's been running for a short time rather than when it's just started? So the catalyst becomes hotter is the first bit, which is not science really, because they've just pretty much given you a clue to that in the question. And once it's become hotter, it's back to collision theory again, because this is part 2 of from the first part. We're using collision theory in part 1, so we're going to use collision theory in part 2. When you see this little part 2, it means it's part of the same question. So when they're hotter, the particles move faster. When they're faster, they're more likely to collide, and then we get a faster rate of reaction. Here, balanced equation for carbon monoxide reaction with oxygen. So we've got carbon monoxide is capital C, capital O, make sure they are capitals, plus O2, it gives us that there. We're putting an arrow in next, which is then capital C, capital O2. And then the balance in it, if we look down here at the mark scheme, you've got to just make sure that you've got 2 of the carbon monoxides to make 2 of the carbon dioxides, because this O2 supplies 2 oxygens, and ideally you'd only really want 1. As you can see from the marks, it's 3 marks. You can get a mark for doing the left-hand side, which is given to you here. You can get a mark for doing the right-hand side, which is given to you here. And then the tricky bit, the balancing, only gets you 1 mark. So don't worry if you didn't get that. It's something we can look at in a revision session if you want to come along and do that. Straight away you look at the graph for this next question. It is looking at endo and exothermic reactions, obviously. It says, explain what the diagram shows about the reaction occurring. Well, we've got lots of energy here at the start in the reactant chemicals, and now we've got less. So I must have given some away. So if I put my hand near that and felt that being given away, I would feel heat energy being given away. It's getting hotter. My clue there then is it's an exothermic reaction. So the 2 points we're looking at there is heat energy is given out, starts high, let's say 100 units, and then here it's like 50 or 20 or something like that. It's got less, so heat energy is given out. That is exothermic. Question 4 then, what's the formula for copper chloride? The information you need is up here. Copper's got 2 pluses, chlorine's got 1 minus. Which do I need more of? I need another minus because I've not got enough pluses yet. So I add another chlorine in. Is that enough now? I've got Cl minus and another Cl minus. That's 2 minus. Hey, that's right, 2 minuses. So we've got the same number of minuses and pluses. That would be 1 Cu. So that's got to be option A or C. And then I want 2 Cls, which means it's got to be option C. For part 2, it says, explain what is meant by a theoretical yield. That is where you do your little calculation and you use the equation to predict how much is going to come out from your reaction. And that's exactly what it says here on the mark scheme. Okay. For part B, bromine reacts with hot iron to produce iron bromide. Write the symbol equation. Again, you've got the starts of it up here. You've got bromine, Br2, you should know it's diatomic because it's like Cl2 and F2 and all the other ones in its group. So we've got Br2 reacting with iron, Fe, and it's changing, so we've got an arrow next, into FeBr3, and they give you the formula for that, which also gives you the clue that it needs to be balanced. Because I've got FeBr3, that's a bit of an odd number, because I've got Br2 on the other side, I've got to look at how I balance it. So I'd quickly think about 2 and 3, what do they both go into? They both go into 6. So if I have 2, and look over here for this bit, 2 FeBr3, I can get 6 bromines, and I can get 6 bromines by putting a 3 here. Because I've got 2 Fe here, I'll have 2 Fe on this side as well. So it's all balanced on that side there. Again, 3 marks, left hand side, right hand side, balance it. Oh, and don't forget state symbols, that's a cheeky little one. It says include state symbols. That's where the 3rd mark is in this one. Cheeky. So we've got solid bromine solid iron as given a clue here, liquid bromine as given a clue here, and then it says solid iron bromide in the top here. So that's nice and easy. For calculating the relative formula mass, they give you everything that you need right here. You've got iron, which has got a mass of 56, bromine, which has got a mass of 80. So we add in the bromine 3 times, and then you add in the iron once, add them all up, and we get 296. Part 3 of the question, you want to work out the percentage by mass of the iron in the iron iodide. So it's given you the total of 310. You want to know how much of that is iron. So if you look at the clue from the last question, iron was 56. So it's just like a test. You scored 56 out of 310. What's your percentage you got? So you do 56 divided by 310 times by 100, and that will give you 18%. Hopefully that makes sense, because percentages are nice and easy, I think. Hydrogen peroxide reacts with some iron compounds. It's H2O2. What's its empirical formula? So it's asking you to understand what empirical formula is. That is the simplest ratio. That's a 2:2 ratio. Can we go smaller? Of course we can. We can go down to a 1:1 ratio, which would be HO, or even OH, or O1H1 or H1O1, as long as it's a 1:1 ratio. Motoring through to question 5, covalent substances. Give the meaning of a covalent bond. This should be drilled into you by now. A covalent bond is a shared pair of electrons, as evidence here in the mark scheme. Properties for that, well, covalent bonds themselves are strong, but if we had another methane copied and pasted next to it, there'd be no bonds between them, so there's no forces at all really between them, or very, very weak ones. So it's dead easy to separate them and turn them into a gas. So that means it's got a low boiling point, option D. It can't conduct because it's not got charge. It has got strong bonds in its molecule, and these A and D are opposites, which should give you the clue that it's got to be one of those in the question. For B, it says nitrogen and oxygen in the air. Describe how you can separate them. So its quickest answer is fractional distillation. How do we do that? They're already gases this time. You looked at it in Unit 1 when you were using oil and you heat it up and they evaporated. Well, we do the opposite way around. We cool them down, fractionally distill them by warming them up, and the nitrogen's got the lower boiling point, which means that's going to come out as a gas at the top, and you can get liquid oxygen poured out the bottom. Part C, graphite is a form of the element carbon. It's giant molecular. Use its structure to explain why it can be used as a lubricant and as a conductor. Okay, it's got 3 bonds where it could have 4, which means it's got 1 electron that isn't in a covalent shared pair, and we are talking about covalent here because the whole question so far, question 5, has been about covalent stuff. Don't even go near mentioning ions. So because it's got a free electron that can move, it can conduct electricity. Why can it be used as a lubricant? Well, because it's got 3 bonds, it forms these hexagonal layers. The hexagonal layers can slide over each other because they've got weak forces between them, not covalent bonds like diamond, which has got 4 bonds and lots of strong bonds. So because it's got, so the shortest answer, because it's got these layers, they're able to slide over each other, making it a good lubricant. And look right down here for an example. You don't have to write much for it. Just down here it shows you exactly how a small amount you can write and still get 6 marks. It's all about keywords like free electrons, forces, current, layers, lubricant, the right sort of words to put in, spelt correctly, capital letters, full stops, 6 marks. Give a use of graphite that depends on its ability to conduct electricity. Well, electrolysis is the easiest. To use graphite electrodes because they don't interrupt or react with anything else that's going on in your chemical reaction. And final question. So looking at the table here, it can get a bit confusing. You want to be reading left to right. So chlorine goes from Cl to Cl minus. It's got 17 electrons in the first place. It's got a minus here because it's got an extra electron, so it's gone from 17 to 18. Sodium is the opposite. It's a metal, not a non-metal, so it's going to be doing the opposite. So sodium's got 10 in its ion, and at that point it's thrown an electron away, so it would have started with 11. In that case, sodium would be Na and Na plus here. For the silver nitrate equation, there's your answers just in case you needed them. For your silver nitrate equation, it's NaCl, because you've got the formula for that going up here, and the AgNO3 it gives you, stick in your arrow left to right, and then they're doing a displacement. So the sodium is getting the NO3 from here, NaNO3, and then the Ag ends up with a Cl. It's already balanced, so it's just a left-hand, right-side sort of thing. Why must you use dilute nitric acid? So it's to get rid of anything else that might be there. You can't use hydrochloric because that would interfere with the test, and the acid destroys anything else there that might give you a false positive or mess up your result. Tricky little one, that one. So it says, explain the results by referring to the structures of these substances when you're looking. So water, for example, is a covalent substance. The particles are free to move around, which is good towards conducting electricity, but there's no charged particles, electrons or ions, so it can't conduct the electricity. Sodium chloride is ionic. Now, as a solid, it does have ions, which would allow it to conduct electricity, but they are trapped in place like solid particles are. They can't move, so they are just vibrating in place. So it can't conduct electricity. When you have the solution, the sodium chloride ions are free to move around, which means that, yes, there are ions that can conduct the electricity, and yes, they can move around, which means that it will conduct the electricity. There's the little summary there. I'm not sure what the grade boundaries are at the moment for this, so I will put those in the description on the video when I upload it online. Just have a look here at the 6 mark section, how little you might have to write, and it's basically what I was saying about ions and if they're able to move.